very essential devices. You'll find them used in many applications, in many other technologies. And one use of them is to distribute the power between two outputs equally. So by controlling L, choosing the right L, we'll be able to distribute the power at output 1 and output 2 equally. And an extension of this coupler is the N by N star coupler. The N by N star coupler cascades a number of 3 dB couplers, the couplers that divide the power equally between the outputs, cascade a number of them to create a star coupler where the input, each of the inputs is equally distributed between the different outputs. And this architecture is used for broadcast and select networks when you want to broadcast a signal. So let's follow here and see if this works as intended to. So we input 1 and 2, they go through the coupler, and for input 1, 50% is supposed to go here and 50% is supposed to go here. So this is 0.5, 0.5. So this 0.5 goes again through a coupler, so then it's 0.25, 0.25. This 0.25 goes again through a coupler, so it's 0.125, 0.125. Okay. And if you follow, let's follow the other branch here, the other 0.5. So here 0.5, 0.25, 0.125. So you can see that for 1 it was distributed as 0.125 of the input for the different 8 outputs. And if you follow any of these, you'll find that yes, the power is equally distributed between the different outputs. Okay?
Now what's the two, are these the 3 dB couplers, two nodes, what are they doing exactly?
They divide by choosing the right L. We make sure that 50% of input 1 goes to output 1 and 50% goes to output 2 at the same point.
So these are inputting to the diagram, the 2 lines at the
No,
top.
no, they are just pointing. Confusing, sorry. So this is supposed to be like an arrow,
Okay.
just saying that these are 3 dB couplers. Is that clear?
Yeah.
Okay. Yeah, this is confusing. This should be a coupler is a reciprocal device, which means that if we use it the other way around, put our inputs here, we'll get the outputs as intended in the input. Okay? So you can see if we put an input here, again, it will leak to the other, and certain percentage will go here and certain percentage will go here. And many of the devices are reciprocal devices. However, in the networks we still need non-reciprocal devices. Okay. Question? Do you have a question? A non-reciprocal device is the isolator. The isolator allows the light of the signal to go in one direction, but not on the other. So how does it work? We can see here a polarization-dependent isolator. So we have our input, which is considered to be at a specific state of polarization. So here, let's say vertical. So it's passed through a polarizer. Polarizer just allows a certain state of polarization. So it will allow the signal to go. If you see here the upper, so here the upper line here shows us how the state of polarization changed as the signal goes through the isolation. So it was vertical. This is a polarizer that allows vertical state of polarization, so that signal was allowed. Then it passes through a Faraday rotator. A Faraday rotator is a device that rotates the signal at 45 degrees clockwise. So you can see that it was rotated 45 degrees clockwise. Then a polarizer of 45 degrees allows a state of polarization of 45 degrees will allow the signal to pass. On the other way, if the signal gets reflected and wants to go the other way, this polarizer will allow it. It will be fine. The Faraday rotator will rotate it 45 degrees clockwise, so it will become horizontal. So then this polarizer will not allow it, so that's why it's locked. These isolators, we need them, or we use them at the outputs of lasers and amplifiers to prevent the signal from going back to the device, which will degrade the performance of the device. Two important key parameters of an isolator are the insertion loss, which is supposed to be very small, 1 dP typically, and the isolation loss, which is the loss in the backwards direction. So insertion loss is the loss in the forward direction. This is the direction we want the signal to pass. So then we need a very low insertion loss. Isolation is the other way, the backwards direction, which is typically from 40 to 50 dP. So this is very close. Okay, that was a polarization dependent isolator. Apparently, we need a device that doesn't work for a specific state of polarization, because state of polarization changes with time. The design obviously would be more complicated, as we can see here. So first, the signal is passed through a spatial walk of polarizer. Spatial walk of polarizer separates the signal into its two states of polarization, the vertical and horizontal. It does that by having a refractive index that is dependent on the state of polarization. So for the vertical, it's passed, as you can see here, with no refraction. And for the horizontal, it's refracted by a certain angle, and that's why they get separated. Okay, so we take both of them are passed through a Faraday rotator, so they will be rotated 45 degrees clockwise. So we'll get these. Then they will go through a λ/2 plate. λ/2 plate also rotates the signal 45 degrees clockwise on this direction and anti-clockwise on the other direction. Okay, so it's different from the Faraday rotator. So again, the signal will be rotated 45 degrees clockwise, both of them, so we'll get these. Again, they will go through a signal spatial walk of polarizer, and so the horizontal will be refracted, and the vertical will pass without refraction, which will cause them to combine again. That's perfect. On the other way, the spatial walk of polarizer will separate the two states of polarization. The λ/2 plate will rotate them this time anti-clockwise, so we'll get this state of polarization, these states of polarization. Faraday rotator 45 degrees clockwise, so we'll get these. And now when they want to pass through the spatial walk of polarizer, so we said the horizontal will be refracted at a certain angle, and the vertical will be passed as it is. And In this case, they will not combine. They will not. They will not be combined. So each one will go in a different direction, which means that the signal, they will not add up, or the signal will not be passed in this direction. Is that clear? Please.
Why do we need to polarize the signal?
It's not something we do. This is one of the characteristics of the signal.
Oh.
Okay, the light or any electromagnetic signal has state of polarization, vertical or orthogonal state of polarization, vertical and horizontal. I can discuss that with you later.
Do we have both? Do we use both of them at the same time, or is it separate cases for each one? For these two?
No, this is the same device.
Okay.
Can you see it's the same device?
So.
But here we show how it works on the forward direction, and here how it works in the backwards direction.
You use it for both. Is this on one go? So it goes to the end and then comes back. Or we can use it in this mode or this mode. The same device.
No, it's the same device.
Yeah.
The mode depends on the direction of the signal.
Okay.
So okay, you have a signal, like say this is the output of an amplifier. Okay, you don't want the signal to be reflected back. So we just want it to go in this direction. You don't want it to part of the signal to come back.
Okay.
So you put this polarization-dependent isolator, it will allow it to go in this direction. When part of the signal tries to go back, it will be stopped. Okay? So they are not different devices or different modes, or it's a device. This direction, it's okay. The other direction, no.
It's the fact of allowing, let's say, like, the spatial walkover, which is the, let's say, the case scenario of the second, the backward.
Okay.
Yes, how will it actually impact where the refractor, which is the front one, in front of the last one?
No, which part? Point.
Yeah. So let's say like when the signal is refracted, because this is an exit. So you look at the scenario whereby the signal receiving some of the signal is reflected, right?
Okay, yeah.
So if it is allowed here up to this extent, how is it going to impact actually the system, the device itself, in terms of performance?
Okay, actually the amplifier, the X5, if part of the signal comes back, it will turn into a laser. So we have to go through how the laser works to understand what exactly happens to the amplifier. But I can tell you that the amplifier will turn into a laser if signal comes back to it. So is this your question?
Yeah.
Yes. So this is just one example of an application where we use these isolators. Circulators are similar to isolators. Just they have multiple ports. So we see here a 3-port circulator and a 4-port circulator. So the 3-port circulator will allow the input at port 1 to go to port 2, and the input at port 2 to go to port 3, and at port 3 to go to port 1. So it will not allow the input at port 2 to go to port 1, for example, or at port 1 to go to port 3, or at port 3 to go to port 2. Do you see? So it's the same concept of the isolator, but extended to multiple directions. Okay. So yeah, we'll not go into the details of that. Just these circulators are very useful, and we will see now that they are used in the add-drop multiplexers. The second or the third, fourth device, very useful device that you can find in many other devices, or it's the block component of other devices, is the fiber Bragg grating. Fiber. The fiber Bragg grating is created by introducing variation in the refractive index of a fiber. Okay, so you can see we have a fiber, the core of the fiber. We have periodically varied the refractive index of the core. So you can see here, the orange color is higher refractive index. So, okay, how does that work? We know that the signal, when it comes to an interface between two medium of different refractive index, it will be, part of it will be reflected. So this is our fiber core. Okay, so we have this signal, a broad signal coming in. This signal, as it goes, as it comes here to the interface between the two media, part of it will be reflected and part will continue. Again, part of it will be reflected. Part of it will be reflected and part will continue. And so on. The reflected part should, or the wavelength that will be reflected, if it meets the condition that lambda lambda over 2 is equal to any wavelength with, or any signal with a wavelength that satisfies this formula will be reflected, and all the reflected signals here will be in phase, so they will add up. Okay, so what is this? The NF is the effective refractive index of the core of the fiber. What does that mean? We know the refractive index. Here we have multiple refractive index. Okay, so this effective refractive index, it reflects or tells us the average speed of flight or the average delay that the signal will experience by going through this core of the fiber with different refractive indices. Okay, so this is some parameter of the system or of the medium itself. This is the the period of changing the refractive index. So for us here it's so a wavelength which is equal to double the refractive index multiplied by the period of the grating period. All the reflected signals here will be in phase, so they will add constructively. Okay? Which will, after traveling a certain distance, we'll find that this wavelength will be reflected out, while the other wavelength will be able to continue. Okay? So if this is our input, a wide signal, our output here, when it adds up, yes, it will be something like a certain wavelength. And the output there will be what?
Everything except that.
Yes. So we will have our band except
And then we add that on to the final field on the sleeve.
no, we don't want that one. Okay?
Or could this be
Yes, so that's why we are doing all this, because we want to get rid of this one. We want not get rid of it, we want to drop it. And we'll see now how it's used in add drop multiplexers. Okay, so we want to allow the rest to go. We don't need them now. We just need this one. So we want to select this one.
it's nothing to do with error or anything like that. We just want that part of the signal.
Yeah, you know, in the area slide, when I talked about add drop multiplexer, and we'll talk about them now. We'll see why we need to select specific wavelengths.
Should the grating period be constant all along? Or can we have the first two different than the second two?
Okay, the grating period itself is constant. What can change is the refractive index. I will talk about this now. Okay, so now how does we create such a thing? We make use of the photosensitivity of the fiber. That the refractive index of fiber will change when it's exposed to ultraviolet field. A fiber with a core doped with germanium has a very, very high photosensitivity. Okay, so what we do is that we put through an ultraviolet signal or two signals that when they interfere with each other, they will create for us a variable intensity of ultraviolet signals. When the intensity is high, then the refractive index will increase. When it's low, then the refractive index will not change. Okay, so we get the fiber, the germanium doped core fiber. We put through an ultraviolet signal or two signals. These two signals, when they interact or when they interfere, they will result in variable intensity field. So the parts of the fiber that are that the high intensity field goes through will result in high refractive index. The ones with the low intensity, they will have a low, or the refractive index will not change. And that's why we get this pattern, periodic change in the refractive index. You are asking if the period should change. No, the period is periodic, but what can change is the refractive index. You can see here the transfer function of the reflectivity. So this is what will be reflected here. Okay, and you can see that small parts of the nearby wavelength are reflected. So if you want to get rid of these, we can design the fiber Bragg grating to have lower refractive index at the edge than the middle. Okay, so just to get rid of these, this is just something for you to know. So this is the reflectivity, and this is the transmission transfer function. So obviously they are the opposite to each other. So this is what is reflected, and this is what is transmitted, as we have seen here, except the wavelength we are interested in. This is how they are used, or why they are used. This is an optical WDM add-drop multiplexer. So in the add-drop multiplexer, we want to drop a certain wavelength. So this is a node. There is some information attended to that node sent through wavelength 2. So this node is not interested in receiving all the wavelength. Okay, because this is a WDM system, we have multiple wavelengths together. Just wants the wavelength intended to it, or with the information intended to it. So what does it do? It drops this wavelength. How? So we use a circulator. We want the input at 1 to go to 2, continue in this direction. Then we'll have a fiber Bragg grating that drop wavelength 2. So then this node can have wavelength 2, extract the information needs from it. And because we have a circulator, we are sure that 1 will go to 2 as we want, and 2 will go to 3. Will not go back to 1, or 3 will go back to 2, or anything. Okay. We can also have the adding element. So this is the dropping. The add will be, and this can happen in the same node. So the same node can receive the wavelength, extract the information from it, and then wants to send more information on that wavelength. So it wants to add it back to the other wavelength on the same fiber. So what does it do? It just uses a coupler. Okay. Any questions? Okay, filters and multiplexers. Filters and multiplexers are, or the wavelength selective components are very important for different applications, for multiplexing and demultiplexing, and we'll see that, and also for filtering noise. Okay, so this is a simple filter, or simple block diagram for a filter. So we have an input with multiple wavelengths. The filter will only allow a certain wavelength and will block the others. We might have a third output where we can obtain or collect the reflected or the rejected wavelength. A multiplexer, as we said, is a device that multiplexes different wavelengths into a single fiber, join them all in one signal that can be sent through a single fiber. And this multiplexer can be built by fusing a number of couplers together. So imagine you have the coupler we have just seen, you have many of them, many fibers fused together, so that many inputs will all transfer to a single fiber. They will all join a single fiber. For routers, when we talked about reconfigurable WDM networks where we can re-establish and reconfigure the connections between nodes, this is where we use routers. So we have inputs. The input to the router will have multiple wavelengths, and each wavelength should be routed to a certain output. This is a static wavelength router. This is when it's configured, when it's made, configured for a certain connection, and it can't be changed. So we can see here we are using demultiplexers and multiplexers. So this is the incoming signal with multiple wavelengths. It's demultiplexed into the individual wavelength. Then each individual wavelength is guided or is taken to a certain input here, or which input to one of these multiplexers, which will lead it to the certain output. So when we design this, when we build it, we will build it that, okay, lambda 1 coming at input 1 will always go to output 2. We can't change our mind later. Okay? So obviously this has very limited functionality. So that's why we need the reconfigurable routers or reconfigurable optical connects to support reconfigurable WDM networks. And we'll see how this works later.
How about the order of the wavelength?
Yeah?
The order, or it doesn't matter?
Order. What do you mean by order?
Like,
Because
do they arrive in
no, they arrive together.
together,
Yes,
even though you're routing it a longer distance?
longer distance.
Or is it equal distance for each one?
No, you mean this interconnects?
Yeah.
These are, this can be just a chip. So it's very small, so this is not a concern. Okay, and so if this travels slightly more than this, it doesn't matter. When designing an optical filter or looking for a suitable optical filter, there are a number of parameters we need to take care of. The first is similar to any other device. We need low insertion loss. Okay, we need the insertion loss to be polarization independent. We also want the passband, the wavelength selected, or to be independent or from the ambient temperature. So over the temperatures that the fiber or the filter can work over, which is up to 100 degrees, let's say, we want the shift in the wavelength as a result of an increase in the temperature. We need to make sure that it's smaller than the spacing between WDM wavelengths. Okay, so as the temperature increases, this wavelength will slightly shift. We need to make sure that this shift is smaller than the spacing between channels. Okay. We need also the passband to be flat. When we cascade the number of filters, this passband will get narrower and narrower and narrower. And just we need to make sure that it's reasonably flat. It's not very narrow, because for the laser over time, the wavelength generated by the laser will slightly change. So we want to make sure that our passband will accommodate for such a change. Okay. Also the skirts of the passbands here, we want them to be as sharp as possible to reduce the leakage into adjacent panels. And this energy, this interference, is regarded as crosstalk. One of the basic filters that we use is the Fabry-Perot filter. A Fabry-Perot filter is created by two mirrors of very high reflectivity. As you can see here, you will have the input signal incident into the left mirror here. So these are the mirrors. Okay, imagine that my hand here is still there. So the signal will come this way to the first mirror, to the left-hand side mirror here. Okay. So this is our input signal. The input signal will be reflected, and it will travel through the cavity. Then at the other mirror, again it will be reflected. Then coming back again, reflected. These mirrors are of very high reflectivity, which means that only a very, very small amount of the signal will go out, will pass the mirror. For those signals of a wavelength equal to for those signals of a wavelength that is a multiple or the wavelength is a multiple of the length of the cavity, the distance here between the two mirrors. When they pass through the other mirror here, after multiple journeys, all the signals will be in phase. So they will add together constructively. Okay, so then this will be the signal passed through the filter. The other signals, whatever is passed here, will not add constructively, they will not be in phase. Okay, so this is the idea behind the fabric ferrite filter. The transfer function, you see here the power transfer function is given as, don't worry, you don't have to memorize this. Where A is the absorption of the mirrors. So A R, the reflectivity. And tau is the one-way journey. So it's the time it takes the signal to travel the length between the two mirrors. So what is tau then? If you want to calculate tau. So tau is the time, so then it's the distance over the speed. And what's the distance here?
L.
L. And what's the speed? Yes, okay, speed of light where?
Between the two.
Yes, but this is not necessary, or it's not vacuum. Okay, so then we should include what? what gives us the relation between the speed of light in a certain medium and the speed of light in vacuum.
The reflective index of the
Yes, reflective index of that medium. So let's see. So C, the speed of light, N, the refractive index of the medium, and L is the length of the cavity. So, okay, then if we want to change the wavelength that is reflected, what can we do? We want to tune the filter. We can either change L or N. Okay. Changing L means that we move the mirrors closer or further, and we refer to this as mechanical tuning, which is considered really to be poor because considered to be really poor because we need to make sure that the mirrors are, as we are moving them, they are still parallel. Any movement will cause poor performance of the filter. And yeah, here, okay. So this is how we tune the filter. You can see here the power transfer function, which is given as you can see here. And we see the power transfer function here for A equals 0. So very low absorption, 0 absorption. Or virtually 0 absorption. And for different reflectivity for R equals 0.99, 0.9, and 0.75. And you can see that as the reflectivity increases, we have a narrower band. So we can reflect, or we can select a certain wavelength, a narrow band. And these are you can see that the pass bands are periodic for any wavelength that meets this. Okay. And we refer to the distance here between the two pass bands, of the filter as the free spectral range. FSR, this is what you see here. Free range. Okay, there are a bit more to say about this refractive filter, but we will discuss it tomorrow.
What's K?
K is the integer. So the wavelength can be multiples of the L. And that's why we have this periodic function transport transfer. V is velocity. So I wanted to show that this is the velocity of light in that medium. And now we are putting it in terms of velocity, the speed of light in vacuum.
It's a round one, right? So equals 1 times all the C numbers in vacuum.
C is speed of light in vacuum.
And N is number.
Now refractive index.
Yeah.
And so tomorrow, is it 2 to 3. Huh? 3 lectures. Oh, on Thursday, no lectures. Huh?
We have this.
I mean for me, it will be this today and tomorrow. We will not have a lecture on Thursday.